going to welcome Sooraj out the front here in a second, and while he's walking out here, I'm going to quickly read out a bit about what Sooraj's talk is going to be about tonight. So, computer noise classification models, including Birdsong classifiers like Merlin or BirdNET, are currently becoming more accessible due to recent advances in mathematics and technology. So, Sooraj, who has a background in systems engineering and acoustics, will talk about how these classifiers are able to identify birdsong and the many strengths and weaknesses these classification models have, while briefly touching upon some commonly used classification models that are available. In addition, Sooraj will also talk about building your own hobbyist ecoacoustic station for your backyard or apartment, which will passively listen to the birds in your area and will also give you a list of the detections and give suggestions on how to improve the classified detections of personal monitoring stations. So, I'd like to put your hand together.
Hello everyone, thank you for having me here. Before I start also, I bought one of my loggers over here. With a mic attached to it. You can distribute it around, have a look, pass it around as you're going. Just pass it around and you can just have a look at it. It's about the size of what you can expect a personal logger to be, something like that.
Explain what it is again.
This is a mini computer with any classification model you want put on it. You want to put whatever on it, you can put. Has a mic, stick it up to a wall, stick it up to your balcony, anything, give it power. It will start recording and letting you know what is on here. Just a small one here. I think it's better if I just show it like this here. But that's going to be a conclusion. So first let's go over a few testing here. Let me know if you can hear this. Wait, no, it's not coming in. Okay. It's coming from the computer again.
It's coming to the computer, it's not.
Important that the sound comes through. Now it's here. If people are hearing it, that's good. Any idea what? People know what that is, right? Okay, any guesses? Of course. Next one, let's go over just to test. Okay, hopefully that's the loudest one then. That's my high noise calibration right there. So won't get louder than that. Okay, we're able to hear. Let's go over a quick thing of what's a spectrogram in the end. So we did see the sound over there, and let me just start playing the sound also over here. It's a robin that's calling. A spectrogram in the simplest way is keeping your sound data. People are familiar with a bar chart like this. Keeping your sound data across all of its frequencies, which is available over here. So you're converting your sound data into an image data, makes it easier to understand. Image recognition, audio recognition is basically in the end an image recognition problem. You convert it into an image. Image recognition has a huge history behind it. You can use it to classify it. An important thing to know about spectrograms is that you see these different bands happening across over here. These are what are called harmonics. So harmonics are, go next, slide. Okay, harmonics are mainly you have a pipe. People who are familiar with music would know this, but you have a pipe, you have a string, anything like that. The string vibrates from one end to another. It could vibrate in the middle, cut by the first harmonic, cut by the second harmonic, cut by the third harmonic, things like that. So a harmonic is basically your sound distribution, your sound energy being distributed over whatever is making the sound. So you do have your spectrum is filled with all these harmonics over here. So whatever the sound is there, it's making the harmonics. These harmonics interact with each other. They can either like waves on a beach. They either crests come together, make it louder at a certain harmonic. Crest or trough comes together, makes it softer at a harmonic. You get these mixing up, and that's basically your spectrogram. So considering that, you can see the spectrogram here. You can see your first harmonic, second harmonic, third harmonic, fourth harmonic. Harmonics are just a way of looking at your sound here. You're seeing how they show up in your spectrogram here. It's just something to be familiar with. Not exactly required if you want to build your classifier, anything like that. But if you are looking at a lot of spectrograms in general, which most sound people should, good to know what a harmonic is. Let's go next into a fairy wren sound. So, if you're looking at this spectrogram here, you can see that it's a pretty standard shape. You're looking at that shape. You break this down and you get it into shapes like this, which is basically something like this wiggling over here. This is a pretty consistent sound. Fairy wrens do make somewhat consistent sounds. They have a bit of variance, but they can be consistent with their sound. A very basic, bare basic, low computational intensive way of doing it is you take your sound and you just run it through a random model like that. Your first pass of a random model, it's not picking up anything at all. These are just this spectrum, the energy distribution of the spectrum over this grid here. First pass, it's not picking anything up. Have it run through a couple different passes, and then gradually you will start seeing that it will start picking up what the pattern is. Same way how people look at patterns, see a pattern, it starts knowing that that pattern is associated with this sound. Easy enough. And then in the future, you can use that same pattern to recognize which call is there. So if you're using that pattern which we made right now, run it across this spectrogram, you get that it recognizes those sounds there. And then since we know that we trained it on a fairy wren, we know that that's fairy wren. This is high level, quick basics thing. Oh yeah, and it is a bit of an older method of doing it. More modern method uses something called audio embeddings, which we will get to soon. About that. Next, let's think about a bit more detail. We have a bit of variance around here. We don't have that exact same pattern. If we go back here, we can see that it missed out. This pattern will miss out something like this, which does not match to the pattern map there. It's going to miss out on all these things. So let's go back into the next step there. So one way of doing this is, let's break it down into simpler pieces. The simplest piece here on this fairy wren trill here would be something like, you could have like any edges, so a vertical edge like this, which you can just get out there. So that is one thing which you can notice easily. Or you could have like a downward sweep like that. Those are commonly repeated things here. So those are easy to identify, easy to pick up. Next, you combine those into how they happen often. So you do see here that that vertical edge happens with the downward sweep almost always. You have a vertical edge, downward sweep, vertical edge, downward sweep. So you do know that these two are coming together. So you have a syllable, what we call the sound syllable, happening over here, which is roughly that shape, what you're looking at. And also you can add in energy values over here. You do know that the downward sweep is brighter on the spectrogram, more energy on there. So you could look at, okay, a vertical sweep with a high energy downward specs thing. You're still identifying your primitive shapes, but now you're identifying the primitive shapes if they happen together. Next, combine them into your whole motif over there. So we do know that this happens repeatedly. You are looking for this pattern over here. In the end, still the same two shapes. And afterwards, combine it with the whole song, add it in, any trilling happens often, things like that. Combine it together. And now you're still identifying basic shapes. There's no hard matching or anything you're doing. You're identifying basic shapes, but because you're running it through different stages, you're now able to identify complex patterns when those basic shapes happen together. This is roughly what we call a convolutional neural network, a CNN. What a CNN does is that you define your basic shapes at the start, or you can allow the CNN to pick out its own basic shapes. Whatever you run through it, CNN simplifies it into your basic shapes and then simplifies how big you make your parts out of it. If you want to do, as I said, image recognition is a common aspect of it, and that's what CNNs were first trained on. So for example, if you're looking for a house or something like that, you start seeing straight edges over there. See straight edges, okay, so you're looking at straight edges. Next, straight edges that show up in square forms, that's either a window or door. You can see that okay, it's either a long square or a more squarular thing. So you can identify whether window or door there. That's your second stage. Your third stage, you can combine them together. And fourth stage, you find future stages, fifth, sixth, seventh stage. All those pieces combined together, you can identify a house. Same way, you combine all these things together, you identify the total trill. And of course, in the end, you can add some additional calibrations to combine it together. Now, let's get back to embeddings. This is the spectrogram data which we pulled out first step. This photo which I'm showing right now is very coarse. You can see it's losing out on all of that trill of a fairy wren over there. You don't see any of that here. But this itself is a lot of data. It's computationally intensive. And it can get very difficult to train large things on, to do anything with it. You need like large computers, whole supercomputers or something like that to run. Getting this to run on a small device like a smartphone or something like that is just impossible. It's difficult. So, chuck them out. You don't need them anymore. What we will be doing is we will be taking that spectrogram and converting it into what we call an embedding. An embedding is, in the simplest form, a series of numbers. It can be about like 16 characters long, or it can be up to like 1,224 numbers. It's just a string of numbers in the end. How we make those embeddings is we take our spectrograms and we run it through either an existing CNN model or we make our own CNN model based on it. That CNN model builds those feature maps of it. So it's building the feature maps in the back, the same way which we made with our CNNs before. And with those feature maps, they get simplified even further. As long as it's the same CNN model, you can convert your string of numbers back into the spectrogram quickly. So you're converting your whole set of data back. So going back here, if you take our spectrogram there, this is just 16 numbers. Storing 16 numbers is way easier than storing all this. Processing 16 number and doing any math on 16 sets of numbers, way easier than this. And if people, since we have been talking about maps and everything recently here, if people can kind of see this, you could kind of see this as coordinates, something like that. Map is a two-dimensional thing, this is 16 dimensions. It's basically the same concept, it's just increasing more and more. Okay, mathematically it's the same concept, and I'm getting into that. You could be using that with either existing models. You have your BirdNET. Google has launched a new one called Perch recently. Avis is another common one that's around, used in a lot of bioacoustic stuff. I think BirdNET is the flagship one for bioacoustics right now. But yeah, you could run it and you could make embeddings based on this model. And afterwards, with this, if you run it back through the same model, you can convert the embeddings back to the spectrogram. Or of course, you could make your own embeddings, your own network, and that's computationally intensive. Now let me get back to how 16 dimensions is actually simple. 16 dimensions is this data set here, it's actually very coarse and very rough, like a rough graph. A proper network or a proper classifier runs up to a couple thousand. I think BirdNET does run to 1024 sets of numbers. And how you represent them, you can't. People are not very comfortable visualizing anything more than 3, maybe 4 dimensions if you add in time or something like that in it. But mathematically and computers, 1 dimension is the same as 1 million dimensions. It doesn't matter. You can just add in as much more data as you want. The same math happens. And here, for example, if I take the first 2 numbers, first 2 dimensions, I can start clustering things around here, put it on what we call an embedding space. Embedding space, I know that my ravens are trained over there, hornbills are there, scrub wrens, robins over there. Oh, I granted this is, you keep in mind this is fake because, as I said, hard to visualize anything more than, on a screen, hard to visualize anything more than 2 dimensions. If I have any future recording, any audio which comes up in the future, I run it through whatever existing program I have, I make an embedding, I get the list of numbers, and I plot it on this. So if I have an unknown data, I plot it on here, and I see how close it shows up with the existing things which I have there. Depending on how close it is, that's much more confident I can be that it is actually the same thing. So this unknown blue point here, pretty sure it's a robin because it's close to the robins. It maps out the same way as the robins. Of course, 2 dimensions loses a lot of data. You need a lot of things there. Now let's go back into a few errors. What can happen? You could have a really noisy event like this at the bottom here, where fairy wrens are present in that, but a model might miss it because it's too noisy, too difficult to pick it up. That's one type of error where you get a false negative error. It misses the event completely. Another thing is you might listen to something like this, which is similar sounding, but actually a different species. So the model might think that this is actually also a superb fairy wren, but it is a similar sounding, but different species. That's what we call a false positive over here. When it thinks it's a fairy wren, it's wrong. These are how we measure our errors. So you either have, these green spots are where you want to be. You want it to, when it tells us a species is there, you want it to be right. And when it tells it's not there, you want it to be wrong. It might miss out on the event, but it might miss out on the event here. It will say that there's no fairy wren, but there's actually is one. It's kind of a waste there, and that's a type of error. It might say there's a fairy wren, and there's actually no actual fairy wren there. That's a different type of error. There is a trade-off there. So when it does have what we call a high precision, that means that whenever it says that it is a fairy wren over there, for sure it's going to be a fairy wren over there. When it does that, it's very likely to miss out on a lot of events where there might be fairy wrens present also. Another way is that you could have a loose model or an eager model where you're like, okay, even if you're unsure about it, put it in. Yeah, you'll be getting a lot of wrong information over there also. It's a bit of a trade-off there. So you could either have a very strict model or a loose model. It kind of depends on what you want to do. If you're just running a logger out somewhere here and you just want to know what species are around here, you want it to be sure about it. So maybe then you would try to push it up to a high trained model like that or a more cautious model. If you're looking for rare birds, like someone was saying me today about like bittern surveys out in like Hexham. If you're looking for a rare bird like Hexham bitterns or something like that, it's better for you if the model actually tells you there's a bittern over there because you're going to be looking at it anyway. You want the model to be loose over there. So it's a bit of a trade-off on how you do it, and that is how you train your model in the end, whether you wanted to pick it up or not. And this is part of the training and part of the embedding process over there of like which embeddings it picks up, which embeddings it chucks out. Alright, now main thing here, Merlin. I'm just going to talk about Merlin real quick because that's the main reason why a lot of you are here. Show of hands quick, who has used it in the last month or so? Yeah, pretty good. Merlin runs off its own model. It's run with Macaulay Library. It's recent after its April update. Right now it has about 200 birds in there, and it's further calibrated by 200 birds in Australia, and it's further calibrated by location. So it has eBird data in the back there, so it doesn't give you like a American robin over here or something like that. So it does have it, and it does have a multi-label classification for classifying your audio. You just keep it recording over there. It will tell you every single thing it hears. It doesn't stop at the first one it hears. By these people here. How Merlin works is that we have there's a team of annotators present across Australia here. Most of them go through spectrogram data uploaded through eBird, and they go and mark out every single species present there. So this is what becomes your training data over there. So we have the main superb fairy wren over there and the background one over there. Also have a magpie lark, a house sparrow, more fairy wrens. Raven is calling over there, house sparrow, some unknown bird over there, things like that. So Merlin is built on this data which annotators build and do. And annotators, there are about like 10-15 people in Australia working on it, working on thousands of recordings from about 700 recorders. Last I checked in, 700 individuals who have uploaded audio to eBird, thousands of hours. So very grateful to all annotators who are building this and are working on it here. And also Merlin needs audio recording. So people who upload audio, so if you have a cell phone, anything, and you hear a bird, record it with your cell phone, put it with your eBird list, same way as you put your photos. And we do have a lot of eBirders who are here who do put in their audio around onto Merlin, onto eBird for Merlin to train on. Of course, most of it is Australia, but we are having other ones in the Australasia area also around here, and recorders over here. How Merlin works is that you have your sound recordings. How the training process works is that you have your sound recordings. Annotators go through, make the annotations, get your species done, things like that. That gets sent into a model for training. So the model trains and it tests on that. So we test and evaluate it afterwards, see how well the model is performing. Afterwards, based on the evaluation, we either refine it, see how the recall is, how the precision is, adjust it for different species. Some species might need a higher recall, some species might need a lower one, things like that. And then decide if it's good for species release. If not, goes back to training. If it is good for species release, comes out how it is. That's Merlin there. Not to say that Merlin won't make any mistakes, even if it comes out for species release. And as I said, we have problem species like this where species do sound similar. Fairy wrens, and not only these fairy wrens, might as well add the other fairy wrens. They all sound like, for a person who has experienced birding, you can kind of pick out the sounds as you hear them. But for a model computer, they look very similar. They sound very similar also. And I mean, people who start out birding also struggle to identify the difference between it. Similar sounding species, we did see. It struggles a lot with it. Another issue is, to be fair though, super fairy wren performs decently well. If Merlin tells you that it's a super fairy wren, it's highly likely it's a super fairy wren. Like 10% chance it's not. It's pretty good, but it does miss out on a lot of fairy wren calls. Another problem issue is just not enough sample data. As said, recordings are needed for this. We need audio training to put it on here. So we have something like Indian myna, thousands of recordings are there. Versus, well, I think it's a little heron now. Little heron or stranded heron now. Just not enough recordings around it. Understandable, stranded heron. Little heron is not a vocalizing species. It doesn't vocalize too much. But species like this, where we don't have enough recordings to train our model, is another thing, which is why it's good to have recordists going around Australia, like I showed earlier, recording a lot of species. Another problem is your sound variance. Some species have a very consistent sound. Some species say whatever comes to their mind. So it's hard when you don't know what to expect. Sometimes you don't know what sound a bird would make. Classic example is if you have a bronze cuckoo, very recognizable call, very easy and very clean spectrogram also you see here. You know immediately that consistent call, and understandably because it's such a consistent call, it is one of our best performing birds in the model. Understandable. Barely, it will always pick up it, and if it tells it, it's almost guaranteed it's a bronze cuckoo. Always, people who are aware of statistics always be cautious about guarantees, but it gets as close to a guarantee as you can. Bring back the myna. A myna add some purring over there. Highly varied. It's so difficult to train a model on this because you don't know, the bird also doesn't know what it's going to say. The computer is over there. The only reason myna is pretty successful in the model is because of the large number of recordings. We do have a large training set available for it. So we have captured a decent chunk of its vocalizations, but look at this. Another problem, and this is interesting, and this is my joke bit over here, so they weren't laughing so far. This is a bird. People would be familiar with the story, but if not, that's a bird. And people are nodding around here. And hopefully we'll make it sound soon. But people are nodding over here, they know already what it is. Lyrebirds. Similar mimics. So, famous story now, everyone loves it. Lyrebird in Taronga Zoo, echo, heard an evacuation siren, loved it, and started playing it everywhere. So, what do you do in situations like that? I would run. If I heard that, I would. So, if I can't ideate as a lyrebird, what am I expecting a computer to do it also? So, mimics are the biggest challenge of any classification model. It's so hard to identify mimics, and it's going to be even harder. As a person, it's hard to identify mimics. It's going to be even harder for a computer. Granted, testing is happening. Lyrebirds do have consistent call sounds, which they intersperse between their mimicry. If you do train for those call sounds, you could technically identify that. We'll see how it goes. There are a lot of recordings. People love recording lyrebirds, so easy. And the big caveat is that I expect a very low recall already for this. The recall is going to be terrible because it's just going to mimic. You're going to miss out on a lot of mimicry, which is understandable. And that should be it. So if you are using Merlin specifically, here are a few of the problems which you will notice. It is still a work in progress. It is being trained in the Sydney area, I said, but this is mostly in all of Australia also. Not all the species are on there. It doesn't know all the species. So even like something really obvious to you in the area, I don't know if you go to painted honey or something like that, probably won't pick it up as well. It will also give you a lot of wrong identifications. It's not fully trained on all the species present in the area. And being a non-Australian product, and it's being trained with like Indian birds, how I got involved with the project, and American birds, things like that, it will lose out to that. So you will get, one of my common examples is that if you're going around here around this lake, for example, here, and if you put Merlin to a Pacific black duck, it will say it's a mallard because it sounds similar. Yeah, because it is trained more on mallards than Pacific blacks. And another technical thing is that it works on the 12 kilohertz or less range, but that's mainly because it's built for cell phone devices. And cell phones are what we call the response chart for a cell phone mic is best within below 12 kilohertz. So high frequency things, high frequency sounds, don't expect bad sounds in this. So things like that. Now let's leave Merlin. Let's go over to a few other models. And I personally am a big advocate for open source models. As much as Merlin is not one, good to talk about here, but there are other models around here also. We have BirdNET, Perch I talked about before, Google, the Google Perch is there, Bird Avis is there. BirdNET is the flagship of ecoacoustics modeling over here now, and it is also, under the hood, Merlin runs an extended BirdNET program, but BirdNET is the go-to model for a lot of these things. So if you are thinking of getting into your own modeling, BirdNET is a good place to start on. And of course, as the problem of open source is that almost everything is just built on people just working on it for the love of the game, I would say, more than anything. So, that's XKCD, but it's open source. If you want and if you have the skills to contribute for it also, please go ahead and work on these projects. They're all on GitHub anyway. So submit code, write things, easy enough to get into that. First thing which I'll go over with BirdNET is BirdNET Analyzer, another model which people can get. This is the flagship one and the easiest one to get into because you don't need any coding for it. You just download it off the website, get your audio files and chuck it in. And BirdNET Analyzer will process it, run it through, get your audio through, and try to do some classifications on you. It is similar to the Merlin list. It is technically different projects, but they are interlinked together. You could also, and it's trained for about 2,000 species worldwide, of which about 200 are Australian. You could start getting it. You could start filtering it, so you could do filters so you don't get mallards over here. Although I have been seeing native mallards out near Port Macquarie, I'm not sure about that, but native. You could see that, but easy to get into. If you are interested in any audio recording, you have a bunch of audio sitting around, get BirdNET Analyzer. It's always good. Another strong part of BirdNET Analyzer is that you could train your own models also with it. So it does have a graphical user interface where you can submit your own audio. Say, for example, that you're struggling to ID bitterns. Again, like I'm bringing that up. Struggling to ID bitterns because bitterns don't have as much audio available in these public models. But you personally have a lot of bittern audio, or you can get them off Xenocanto or something like that. Get your audio, understandably with licenses, so ask people if you're flicking them off Xenocanto, but put them into BirdNET. BirdNET builds these embeddings on their own. So you could use BirdNET model to build these embeddings, and you could use it to build your own classifier. You have a lot of bittern noises, get a bunch of bittern recordings, put it on BirdNET. It's all a graphical user interface, so no coding needed. Put it on there, it builds this embedding, and you can start classifying it on anything you want. Of course, that's your personal model now, it's not the global model. But seeing it as that, you can use it for not only bitterns, you can use it for any audio basically. And BirdNET has been used for wolves in the Sierras, people use it for whales in Japan, things like that. So frogs, bats, anything you want. I personally have used BirdNET as part of my work for crane noises. So I work as an acoustic consultant for construction companies, mainly the person who makes sure that citizens don't complain when the construction gets too loud or something like that. And one of the common problems we have is crane chain noise. Whenever a crane is lifting up something like that, so this is a site, one of our company sites in Melbourne, I'm not going to specify which one, but whenever a crane picks up something, chain crackling sound against it. If it's picking up, like here, it's picking up a small cherry picker, but then if it's picking up like a shipping container or something like that, the chain banging sound happens. It resonates, it spreads, people complain. None of us in the office wants to sit through like thousands of hours of recording to listen to which one was a chain sound, which one was not a chain sound. Please don't make us listen to that. Run it through a BirdNET model. Might as well. Try it and run it. And we have had decent success with it. BirdNET builds the embedding. It's the same model. It's, technically building an embedding for ecoacoustics, but it doesn't matter. I'm not using it for ecoacoustics. Builds your embedding, you have your recordings, you have your model training, and then just whatever data you get from our side over there, just run it through, and it gives us timestamps of when the model picks up a chain clanging sound or something like that. Then we can personally go in and verify that for whatever compliance reason we have to do. Any sound you want that is repeatable, consistent, chuck it into a model and run. And because of this power, BirdNET has a lot of active projects around the world. This is picked up from BirdNET's website itself, so you can check it out over there, that link on the project map. Yeah, it's mainly North America and Europe because that is the forefront of bioacoustics work in general. But we do have a few projects in Australia also. I think I saved. Yeah, so there's a PhD project going off in Blue Mountains and the Regent Honeyeater project of Taronga Zoo. BirdNET projects right here. If it's good enough for them, it's good enough for you. So just pick up whatever audio you want, chuck it in, run it, should be good. Next thing which I'm coming to now here is a pretty big forefront and everyone wants it, and that is unattended monitoring. You don't want to be there. You just want to set up a mic over there and listen. Let the mic listen. You don't want to show up there. You want the mic to tell you what birds are there, what animal is there, what chain clanging is there, anything like that. So as soon as people realize that unattended monitoring is something that is possible, everyone wants it. And understandable. Sending a person out there is just too much effort, too much money, too much hard work. Sometimes it's not accessible to send a person over regularly over there. And it's not only in acoustics also, it's in any field. So this is one of my company's loggers on a Sydney train corridor. Here is the same device as this, but inside a waterproof cage. That's in a waterproof case. That's been spliced up with the battery pack from here and the mic from there. It's there recognizing train passbys there, so we can know specifically what trains are making what sound, so we can do for specific compliance issues there. Any kind of monitoring, having a monitor out there is both cheaper and easier than having a person out there 24/7. Just makes sense. So once this is possible, start running it. And oh yes, of course, if you are setting up things like that, do check your local laws and everything. There are NSW privacy laws that are protecting people. Do it on your own property or contact the property owners. These are done with permissions, things like that. If you want to do unattended monitoring for birds, plenty of products are out there already. You can have your bird weather PUCs over there, which I was talking about with the person today. We also have things like haiku boxes or audio mods around here. There are quite a lot of products around there, available, easy to get. Just order them online and they come home and just set them up wherever. And they are perfect. In the end, they're basically just a simplified computer running with a mic and some form of communication, either Wi-Fi or cellular, something to connect to whatever else you want it to connect to. They're easy, quick. You don't need to know anything about the models. You don't need to know anything about electronics. Just buy them, set them up, and go. They're built for convenience. Sometimes they do come. They are a bit pricey, and I have seen people complain about how expensive they are for what they are. which is understandable. You're paying for the convenience. Or you could, if you don't want to pay for the convenience, you could build something like this, which is over here if you want to go over. This is actually the same devices over there, but I do have a few other ones around. All you need is a computer, any computer you want to run your model. It could either be a mini computer like this Raspberry Pi, or like IBM, Lenovo make like small mini full desktops over there. I personally have one running at home right now on an old laptop which I flicked from somewhere. So any computer you want just has to compute. That's the thing. So it's not exactly a difficult barrier to get over. It's just get a computer, set up whatever model you want. I personally would recommend BirdNET Go. BirdNET Go is another open source project that is not, it's using the BirdNET model, but not the same people. It's a different program. It does take a bit of setup to do so, but it's pretty easy to check online if you want. But that's it. Run it on there. You can attach any mic. This mic, which I'm attaching onto this one here, which I've shown here and in the photo there, is a mic I got for $1 from AliExpress. I got a 15 pack for like $12 per shipping, so might be even less than $1. And I've been using it for a lot of things. So could be the cheap mic which you have. If you have a fancy bioacoustic station, if you have like a parabolic or something like that, hook it up to that. It doesn't matter. Any mic you want, hook it up, could be fine. If you have door cameras or like surveillance cameras around that record audio and broadcast audio, which a lot of people do anyway right now, you can set up the audio stream there if it's as long as on the same network. You can set up the audio stream and just have your classifier lying somewhere in your basement, and it's listening to all the webcams around and identifying which birds are on there. It's pretty easy. So you just turn it on and you start classifying. Let me get over to BirdNET Go. So BirdNET Go specifically, and these classifiers give you an output something like this, which is very easy. That's yesterday's date, right? Yes. Yeah. So that's yesterday's date. So this is when I took the video clip, was yesterday evening. This is the BirdNET Go's interface. Can be customizable. There are a few small things which I have programmed in myself onto this. But if you do get an out-of-the-box BirdNET Go, it will be roughly similar to this. You can have your recording here. You could have your historical data there. So you have previous days over there. If you are suspicious about something, like I'm looking at this, I'm like, oh, what are those nighttime lapwings or something like that? I click on it, gives me my thing, and gives me which model picked it up. This is a custom model, by the way. It's not BirdNET's out-of-the-box model, but still, my model says it's pretty confident that it's a lapwing. Says it's almost good, and I can check the spectrogram, listen to the audio. I'm pretty sure that's a lapwing, but that looks such a lapwing. It's for sure a lapwing. But I can check that here. I can see it. If you are more data inclined, or if you're more like you like seeing your recordings. Actually, no, before this, it'll be going over. So it'll go over your historical records also here. So latest identified species, in which things, a lot of lorikeets, miners. This was done in the evening, so dusk chorus is going on right now. If you are analytically inclined, there are analytics panels present also there. So it does say what recordings you have got, how often you've gotten them. You can see that it's all cockatoos in my area, so it's really loud. But yeah, and then you get your list of recent recordings, list of species that have been detected. This should be in the past. This logger was running for this presentation, so that was only about 2 days of data. So here you can get your list of birds. All this is mostly out of the box, so you don't exactly need much to get going. You can just build this yourself. And yeah, here you can see your distribution across the day. So I can start saying that my dawn chorus over there is primarily a lot of butcher birds, magpies calling a lot. Rainbow Lorikeet, it's pretty consistent throughout the day. Occasionally, I will get like the night lapwings, which is actually expected in the area. I live across from the children's park, and lapwings come there at night and wake me up. So it's expected. But you start getting trends like this. I see my butcher boys during the dawn crawl chorus, but then a lot of numbers there, but then very little over there. My cockatoos are everywhere. Cockatoos are everywhere at my place, so it does give you good data, and you can build this up yourself. And my cockatoos are everywhere. Every single dot there is a cockatoo. So it's pretty useful. You could get it. A bonus if you do build your own device like this is that you can choose how to customize it yourself also. A bigger problem I've seen a lot of people complain about audio mods or haiku boxes or things like that is that they are difficult to customize. They are very good if you are just getting into bioacoustics or just want to get some data fast. But if you are getting a bit more into the nitty-gritty of the models or things like that, you want to get some more control over it. So it's your own data if you build your own models. You can add in your patterns if you want, you can add in your fairy wrens, add in whatever you want, add in anything, add in wolves, add in whales, whatever you want. As long as the audio reaches the device, the model will pick up anything. And if the audio reaching the device is a problem, you can use your own recording setup. You have a $1,000 mic, sure. If it's perfect studio quality mic, sure, attach it on and it will record, it will classify, you'll get your details there. Or if you just want to go pure budget and get a cheap mic, sure. It's your choice in the end, it's your model, it's your computer. So whatever you want to do, you can do. Anything you want, you can classify it. Doesn't matter. You're not limited to birds or like in a haiku box or something like that. You're not limited to these things. You are free to do whatever you want. And if you have questions or anything like that, you can add it. So this one here, I didn't bring it with me, but when I do send it out on site, I do attach a little USB dongle for SIM cards, and I just put a SIM card in, a $15 Aldi SIM for a month, and it gives me all my data. So whatever you want, or if you're on Wi-Fi adapter, however you want to build it, it's easy. And sorry, okay, I shouldn't say it like that. It's customizable. You can build whatever you can think of doing. You can pretty much do it with this here. So your creativity is the limit over there. So, and I know most of you are very creative people, so please go ahead. And of course, if you want any of this data, how you want to store this data, how you want to process it. So on this device specifically, and the data I showed you over here, I personally run it through what is called a Postgres server. It's a pretty old, people who are familiar with it would be familiar, but it's a very old, pretty standard way of storing data. I host all my data through a website. It's online somewhere. If you find it, you find it. If not, then sure. It's not exactly looking for traffic over there, but you can post it on a website. You can push this in. Data, you can do whatever you want with it. You can host it. And thinking of hosting over there, just the last end of talk honorable mention project over here, which I would want to talk about, is bird weather. Bird weather, I think people are using it in Newcastle area. Last I checked, it keeps records since 2021. It's a pretty easy API. The web API is there. You hook up any of your models to most of the classification models. You can hook up to bird weather, and it broadcasts your sightings, your sound. It takes the clips. You can even, if you choose, you can even upload the clips of specific detections. So if you want to say that, okay, every single noisy minor detection, put it up to bird weather. I don't care about the data storage. So you can do it. And cool. There are about 20,000 stations around the world last I checked. I think this was last week. And if you are more interested in the data processing over there, there are quite a lot of APIs and data management stuff to both manage your own data and other data which people have contributed onto bird weather. The reason I talk about this is the bird weather PUC, which I didn't mention before, is built for this thing. It's easy enough to link it up to that. So if you do buy a PUC, and I know some people in Newcastle have it, I don't know if they're in the room with us or not, but it's easy enough to link up to bird weather and we can share. Bird weather looks something like this. It's a global map and you can zoom in, and I'm zooming into Newcastle, hopefully if I remember right. These are all the logging stations around. The dark green ones are the PUCs, which are bird weather's custom ones. The light green ones are ones running people's custom models. So custom hardware, custom software, not sure what you're getting from that. You can see what species are seen in this area, couple of species seen in the area here. Specifically, if you want to see a noisy miner, what noisy miners were seen, these areas, which specific station over there, you have the sounds, you have the spectrum over there, so you can see it, and you can also play it over there. So bird weather does store all this data for it. It is a pretty powerful project, and it's personally one of my favorite open data projects around. Around in Sydney also there are quite a few, so some of my loggers are also out here. If you know where I live, then why do you know that? But second, you can identify where it is. So it's easy and there's a lot of support online. I shouldn't say it's easy, but there's a lot of support online if you are wanting to get into this. And since there's so much support online, it is the best time to get into it also. These models are getting more and more better. The mathematics behind it is improving. Computations are also getting smaller, so you can have small devices like this around. Just build your own, put your data up. But nothing, they're quite cheap also. So this specifically is actually my expensive one, even though I say it's cheap. It's about $200 for the Raspberry Pi and $1 for the mic, so 201. I have a battery pack also, which I plug it onto if I want to use it, but it's a USB-C connection. Your own phone battery packs, the external battery packs can connect to it. It's pretty easy to build and tie together. Ones which I send out on site, like other places, are the old Raspberry Pi, I think Pi 3, and they were about $80. So quite easy and good to build. All you need in the end is just a device. A small device or big device, doesn't matter, or a device to run your computations. So even if you have an old laptop or a computer that's just sitting at home, and use that instead, and something to feed audio in, and you have devices like this, easy to build.
Look at that.